Hello everyone. Again, welcome to the second part of our webinar series regarding point-on-wave switching. My name is Rosemary Sun. I have been working in the field of substation automation and protection for more than 30 years with different roles and have lots of experience both in technical and market side. Today, together with our expert, Yeshon Sulaimanov, we will present you the overview of point-on-wave switching based on Siprotec 5. Yeshon is our promoter and the technical expert for high-voltage protection. Please note that you will not be able to pose your questions directly during the presentation. Nevertheless, you are already invited to insert your questions in the Q&A box located in the top right corner of the window once you exit the full screen mode. Simply switch from the Chat tab to the Questions tab and insert your questions there. Directly after the session, our expert will address your questions during the Q&A. If we should run out of time during the Q&A, questions which have not yet been answered will be answered separately. Furthermore, you will have access to the on-demand recording of this webinar right after the session. Yeshon, now the stage is yours.
Thank you, Rosemary, for the introduction, and good morning everyone out there. It's a pleasure for me to conduct the second part of our webinar series about point-on-wave switching based on Siprotec 5. Our second part is called the parameter settings. As I have explained in the first part of our webinar, point-on-wave function belongs to the function group circuit breaker. As can be seen on the right side, the function point-on-wave switching can be found under function group circuit breaker 1.3-pole folder point-on-wave switching. Per drag and drop, you can insert the function in circuit breaker in the project tree as shown on the left-hand side. Before we go into the details, I want to mention that one point-on-wave function costs 200 function points. So here you can see how point-on-wave interact with control. Generally, there are three different ways of starting. Point-on-wave can be started from HMI, remote station, Dixie, or using some internal CFC logic. Once it is started, then it goes through the function block control. Control will start then point-on-wave function internally. There is one parameter I would like to mention here. This is so-called 3-pole switching allowed, the parameter number 2671102. There are some cases in practice where this could be necessary. You can set this parameter to yes or no. If you set this parameter to no, then the following is valid. If conditions for point-on-wave switching are not fulfilled, for example, reference voltage is missing or trigger command from control is not given, then 3-pole switching is not active, meaning no 3-pole closing or 3-pole opening is possible. If you set this parameter to yes, then the following is valid. If conditions for point-on-wave switching are not fulfilled, then 3-pole switching becomes active, meaning 3-pole closing or 3-pole opening will be executed. If, however, the conditions for point-on-wave switching are fulfilled, then switching command will always be sent according to point-on-wave switching angles. In this case, the parameter 3-pole switching has no influence on point-on-wave function itself. Okay, once you have inserted point-on-wave function in your device, the next thing to do is to connect current and voltages. Here on the slide, the reference voltage is connected to Vsync 1. This voltage can be one-phase or three-phase voltage. In our case, this is one-phase voltage. Normal three-phase voltages and current for monitoring are connected on the load side. These are also routed with placing X in the corresponding field. In the function group connection, under voltage measuring points, you can define where voltages are physically connected to the protection device. Also, you can define whether phase-to-ground or phase-to-phase voltages are connected. In our case, it's phase-to-ground voltages. In the current measuring points, you can also indicate where the currents are physically connected to the protection device. On the right-hand side of the slide, there is a graphical representation where reference voltage and monitoring voltage and current are connected. Please note the following. As a reference voltage, you can connect VA or VB or VC or VAB or VBC or VCA. This must correspond to physical reference voltage connection to the device. However, the point-on-wave function will always calculate the switching angles using phase A voltage as a reference voltage. This means if you have connected voltage AB as a reference voltage, the point-on-wave function will recalculate internally to the voltage in phase A. After you have finished with voltage and current connection, you can go directly to point-on-wave function. As mentioned earlier, the point-on-wave function can be found under the function group circuit breaker. The point-on-wave function DIC is divided into 3 groups: general, opening, and closing. So let's talk about the general setting first. General setting consists of 5 subparts: general, switching angle opening, switching angle closing, measuring transducer, MT, and supervision. In the general part, you can select the application. You can select from the following option: capacitive load, transmission line, reactance coil, transformer, or user-defined. Once you have chosen the application, the next thing to define is grounding. Here you have 2 choices: grounded or isolated. Once you have defined these 2 parameters, switching angles for opening and closing are automatically proposed. You can also define zero crossing direction. You can choose between rising, falling, or both. It's used to determine the time to zero. This parameter is active for both stages, opening and closing. The important point is that switching angles are defined to phase A of a reference voltage. Therefore, these settings refer to phase A of the reference voltage. These angles are recommended, but you can of course correct them according to your needs. 4th subpart is MT configuration, which stands for measuring transducer configuration. Here you can connect all additional signals like temperature, circuit voltage, reference contact, and pressure. These signals are optional and used for the compensation if you need to adapt your switching time according to the ambient condition on site. I'll explain this part later more in detail. So in the last part of general setting called supervision. These are frequency limits, minimum voltage reference, zero crossing of the reference voltage. 2 types of messages can be issued: error frequency or error zero crossing. If one of the messages is issued, then point-on-wave function will not be switching each phase individually. If 3-pole switching allows set to yes, then 3-pole switching takes place. If 3-pole switching allows set to no, then no switching will take place. So let me explain to you why the switching angles has been proposed. Let's have a look at the closing of the capacitor bank with grounded system first. Here, first phase A is closing at 0 degrees, in other words, at zero crossing of phase A of a reference voltage. This is correct for the capacitor because the voltage of phase A of the capacitor is 0 before closing. Next, phase C is closing at its voltage 0 crossing or 60 degrees of phase A of a reference voltage. Last, phase B will be closing at its voltage 0 crossing or 120 degrees of phase A of a reference voltage. Now let's compare to the capacitor closing in isolated star point. As there is no connection to the ground, then closing one phase will not lead to the current flow in this case, because there is no path for the current. Therefore, in isolated systems, the difference of 2 voltages will be applied. For the capacitor bank, phase A and phase C will be connected at the same time, where voltage VCA is 0. This will be at 30 degrees of phase A of a reference voltage. Closing phase A and C at 30 degrees of phase A is ideal because there is no delta between the capacitor and the infeed. As last, phase B will be connected at its voltage 0 crossing, or in other words, 120 degrees of phase A of the reference voltage. So let's now have a look at the closing of the transformer in the grounded system. Here, phase A will be closed at the maximum voltage, or in other words, at 90 degrees of phase A of a reference voltage. This is the ideal point for closing the capacitor because at this point, the prospective flux dashed lines of phase A is 0. Phase B or phase C will be closing at 180 degrees of phase A of a reference voltage. This is the point where the prospective flux of both phases are opposite to each other and in sum 0. Now let's see the closing of transformer in isolated system. As already explained in the previous slide, in isolated system you have to start with closing two phases in order to create the current path. Therefore, here the ideal time to close phases A and B is at VAB maximum, in other words, at 60 degrees of phase A of a reference voltage. At this point, the sum prospective flux of both phases is zero. Last, phase C is better to close at 150 degrees. At this point, the prospective flux of phase C is zero. After we have clarified with switching angles, let's move now to another important parameter for closing and opening. In this slide, we will talk about the parameters for point-on-wave closing. Generally, there are two times need to be differentiated here. One is calculated time, another is measured time. Calculated time are calculated based on the equation on this slide. Measured time is measured by means of current, voltages, auxiliary contact, or reference contacts. The difference between both, called delta, must be small. The first parameter you must enter is CB closing time for each phase. These are the parameter numbers 105, 106, 107 on the right bottom side. These parameters are available from circuit breaker data. Also, pre-arcing time for each phase must be entered. These are the parameter numbers 108, 109, 110. On the diagram, you can see the blue arrows, which are showing graphically measured CB closing time. This is the time from issuing close command until first mechanical contact. First mechanical contact is measured either with auxiliary contact from circuit breaker or with reference contact. A reference contact is used only for Siemens Energy circuit breaker and is connected via fast transducer input of IO218 module. Auxiliary contacts are connected via standard binary input in IO202 module. The calculated closing time will be defined according to the equation in the middle. T close equals T close setting from parameter settings minus T correction plus T compensation temperature plus T compensation voltage plus T compensation pressure. That means the calculated closing time will take into account all the compensation if they entered, as well as the correction time. The compensation time are normally available from circuit breaker data. Correction time are adjusted during the commissioning on site. Correction time are entered at the parameter number 115, 116, and 117 on the bottom right side. The most important time for point-on-wave closing is make time. On the diagram, you can see the red arrows. This is the measured make time. It is the time from issuing close command until first electrical contact. First electrical contact is measured either with voltage or current on the load side. Later I will explain where you can set the threshold. The calculated make time is calculated based on calculated closing time minus pre-arcing time. The calculated make time is used by point-on-wave to send the close command via its high-speed output. Pre-arcing time is the time from ignition of pre-arc until third mechanical contact of the circuit breaker primary contacts. So if you are intending to define circuit breaker closing with voltage, then you should choose make time detection via voltage and enter threshold values for each phase. Please keep in mind threshold values must be exceeded for at least 3 milliseconds for 50 Hz application. If you are intending to define circuit breaker closing with current, then you should choose make time detection via current. The threshold can be entered under circuit breaker general parameter current threshold CB open. The measured time must also be over the threshold for at least 3 milliseconds for 50 Hz. So let's now talk about the compensation factors for point-on-wave. Here you can see the graphic on the right side with temperature compensation. General approach is the following. If the ambient temperature is warmer, then the switching time is faster. If the ambient temperature is colder, then the switching time is slower. As I have explained in the first part of the webinar, you can use IO218 module to connect the temperature. As an example, you can see that parameter number 104, MT for temperature, is configured to connect the temperature on MT4 transducer input. Then you can define whether to use linear or user-defined characteristics. Here you can see an example of user-defined curve. You can then build your own curve. Important to mention is that you need to define the reference voltage for temperature compensation. This can be entered in the parameter number 121. The temperature is set assuming nominal 100% control voltage over the defined temperature range. So You need also parameter transducer input for temperature compensation in the function group analog units. You can define upper and lower limits, also limit for the sensor itself, unit and measuring window. On the right hand side you can see a terminal diagram of IO218 module. One thing to mention here, with IO218 module you have 24 volt power supply integrated in the module. This can be used to supply external devices. So on this slide, control voltage compensation is shown. On the right hand side you can see the linear graphic of voltage compensation. General approach is similar to the temperature compensation. Higher voltages, faster switching time, lower voltage, slower switching time. Parameter number 106 MT for opening circuit voltage and parameter number 107 MT for closing circuit voltage can be used for voltage compensation. Under compensation data you can decide whether to use linear or user-defined curve. In case of a linear compensation, the following equation on the bottom is used. Slope equals the delta time difference between extreme 85% closing time and nominal closing time divided by the voltage difference in percent multiplied nominal voltage in volt. It's advisable to do the calculation at ambient temperature 20 degrees. In this case, the delta time is 5 milliseconds, as you can see on the graph. So 5 milliseconds divided to 15%, the difference of 100% and 85%, multiplied to 220 volts, gives us minus 0.15 millisecond per volt. This can be entered as voltage compensation factor under parameter number 122. Like in the example with the temperature, you need also parameter transducer input used for voltage compensation in the function group analog units. You can define upper and lower limits, also limit for the sensor itself, unit and measuring window. On the right hand side you can see terminal diagram of IO218 module. Here the voltage inputs are connected to the terminals A1, A3 or A5, A7 or A9, A11. The next topic I would like to mention is called rate of decay of dielectric trend, shortly RDDS. This is important for closing of the capacitor bank. RDDS is used to determine the pre-arcing time. There are two RDDS curves on the diagram, S1, which is red, and S2, blue. The difference between both curves is the switching time. S1 closes at 0.4 milliseconds earlier than S2. This can be seen from the graphic where both curves intersect x-axis, S1 at 14.6 milliseconds, S2 at 15 milliseconds, so the difference is 0.4 milliseconds. The point where they intersect x-axis are the point where the circuit breaker is making first mechanical contact. This is the end of closing time. At the vertical axis you can see the voltage is indicated. At the beginning the RDDS is big because mechanical contacts are far apart from each other. As CB starts closing, RDDS voltage is decreasing as contact gap decreasing. Pre-arc usually occurs when voltage, which is black curve on the diagram, is exceeding RDDS curve. In our case, the black arrow indicates this point for S1 curve. This is also a point where first electrical contact is made. As can be seen, from the moment of first electrical contact until first mechanical contact, we have a pre-arcing time of 3.1 milliseconds. For point-on-wave closing near voltage zero crossing like a capacitor bank, this is a problem. You can see that at the make time, the voltage is around 1.2 pu. When current starts flowing through the capacitor at this point, this will create transient on the capacitor. This can, of course, damage the capacitor. Therefore, it's advisable to move the curve from S1 to S2. You can do that if you close circuit breaker 0.4 milliseconds later. As you can see, in the case of S2 curve, voltage exceeds the S2 curve at 14.8 milliseconds. At this point, we have a voltage of only around 0.1 pu. In order to adjust such curves, you need simply recalculate the time in degrees. This can be done using the following formula. Angle equals difference of S1 and S2 multiplied to 50 Hz multiplied to 360 degrees. In our case, it is 0.4 milliseconds, which gives us 7.2 degrees, which means you need to add 7.4 degrees to our standard switching angle. You can enter these angle values on the phase shift clothing for all three phases accordingly. Okay, now let's move to the next topic, which is circuit breaker opening. Like in case of circuit breaker closing, here also two times need to be differentiated. One is calculated time and another is measured time. The first part you must enter is CB opening time for each phase. These are the parameter numbers 105, 106, 107 on the right bottom side. These parameters are available from circuit breaker manufacturer. Also, pre-arcing time for each phase shall be entered. These are the parameter numbers 108, 109 and 110. On the diagram on the left-hand side, you can see the violet arrow, which shows graphically CB opening time. This is the time from issuing open command until first mechanical separation. First mechanical separation is measured either with auxiliary contact from circuit breaker or with reference contact. A reference contact, as you remember, is used only for Siemens Energy circuit breaker and is connected via fast transducer input of IO218 module. Auxiliary contacts are normally connected via standard binary input in IO202 module. The calculated opening time will be defined according to the equation in the middle. T open equals T open setting from Dixie minus T correction plus T compensation temperature plus T compensation voltage plus T compensation pressure. That means the calculated opening time will take into account all the compensation as well as correction time. The compensation times are normally available from circuit breaker data. Correction time are adjusted during the commissioning on site. Correction times are entered as parameter numbers 115, 16 and 17 on the bottom right side. The most relevant time for point-on-wave opening is break time. The calculated break time is used by point-on-wave to send the open command via its high-speed output contact. The calculated break time is calculated opening time plus pre-arcing time. Pre-arcing time is the time from mechanical separation until first electrical separation. On the diagram, you can see the red arrows, which are showing graphically CB break time. This is the time from issuing open command until first electrical separation. First electrical separation is measured with current on the load side. Please keep in mind that the threshold value for circuit breaker opening current threshold is located on the general setting of the circuit breaker. You can find it as a current threshold CB open under parameter number 112. And the next topic I would like to talk is called rate of rise of dielectric strength, shortly RRDS. It's important for circuit breaker opening generally. The RRDS is a slope in volt per second. It's drawn as blue dashed curve on the diagram. As you can see from the diagram, the RRDS start increasing as soon as CB poles are mechanically separated. The increase continues until the CB poles are at the maximum separation. This is the end of movement. From the beginning of RRDS, you can see the arcing takes place. The arcing will stay until the current passes through the zero crossing. This is the end of arcing time. It's also a moment when electrical separation, also called break time, occurs. Now the voltage across the CB poles, green dashed lines, appears. It is important that this voltage is lower than RRDS. Thus you can avoid reignition or restrikes. So now we came to the end of the second part of our webinar, parameter setting. Thank you for your time. Hope you have enjoyed my presentation.
Thank you, Yehun, for a wonderful presentation. I think the auditorium has already got enough knowledge regarding the point-on-wave function. So here comes several questions need to be answered. The first one is, what voltages can be connected as a reference voltage?
Yes, any one-phase or three-phase voltage can be connected as a reference voltage. It can be line-to-ground or line-to-line voltages. And in case of one-phase voltage, you can use phase A, phase B, or phase C voltage. Point-on-wave function internally will recalculate using phase A as a reference voltage. Yes.
So, okay, understood. Here comes another interesting question. Circuit breaker closing criteria Y voltage or current, are these values RMS or instantaneous values?
This is a good question. These are the instantaneous values. Remember, the threshold value must be exceeded for at least 3 milliseconds for 50 Hz application or 3.6 milliseconds for 60 Hz application.
Okay, understood. And here's another question. What kind of signals can I connect to IO218 module?
Yes, to IO218 modules, you can connect directly 300 volt DC, 3 fast 0 to 20 milliamp, 4 standard 0 to 20 milliamp, or 1 RDT temperature sensors. 2 core or 3 core sensors are supported.
Okay.
Also, IO218 module has 24 volt power supply on it, which you can use to supply your converters or sensors.
Okay, understood. And here's another question. Can I change switching angles for opening and closing? Interesting, huh?
Yeah, this is a good question, yes. Yes, of course, you can change the switching angle for opening and closing. The angles that are in the Dixie 5 setting, these are just proposed settings, but you can, of course, change them according to your needs. But if you need to do some fine-tuning of the angles during the commissioning, then it's better to use the correction time for this.
Okay, understood. Nah? So there's another question here. How to understand time delay setting for the reference contact?
Yeah, this is a very good question and mainly also asked from the commissioning people. And the sign for the time delay shall be set as following. If the measured closing time is coming later than the calculated closing time, that means reference contact are coming later than expected. In this case, the time delay shall be set as negative. And the other way around, if the measured closing time is coming earlier than the calculated closing time, then time delay shall be set as a positive. The value of the time delay is actually the difference or the delta between measured and the calculated closing time.
Okay, thank you, Yeshan. Then there comes another question here. What is the acceptable delta value between measured and calculated time?
Yes, the acceptable delta value between calculated and measured values is around 1 millisecond.
1 millisecond, yeah.
So if the delta more than 1 millisecond, we recommend to enter some correction time during the commissioning to adapt the delta accordingly.
Yeah, okay, thank you. Then we have, last but not least, a question. Can point-and-wave function be used for 3-pole circuit breakers?
Yes, currently it's not possible to use point-on-wave function for 3-pole circuit breakers, but however, this is on the roadmap of the development.
Okay.
So we are working on it.
Okay, good. So that's all for all the questions. For the remaining questions, we have to answer it by email. So thank you very much, Yehan, for the webinars and also the Q&As. So dear auditorians, so I hope that you enjoy the point-and-wave function in Siprotec 5. So I wish you a good time and stay safe.
Yeah, thank you.
Bye-bye.
Bye-bye.